Hi folks, welcome to the Defect Chemistry of Ceramics course. In this coursework, you will learn the very basic concepts of defect chemistry of ceramics and the application of those basic concepts to the real solid. But here, I would like to make our systems as ideal as possible. So eventually, you will learn the defect structure of impure non-stoichiometric compound, which is the most general case. Okay, so in this lecture number 1, I would like to tell you why you have to learn defect chemistry and what are defects and how to classify defects, and finally, thermodynamic stability of defects. Okay, why do we have to learn defect chemistry? You see, well, we ceramists have a really chronic headache. That is, there are too many variables which decides properties of a ceramic or performance of a device thereof. But once we know this black box, which controls the causality between these two things, then we will be happy. But unfortunately, we do not know what this black box is. This is really black box. So pure scientists quite often, refers to the ceramics as the bake and shake. You know what it means, heating and shaking. And also they refers to the metallurgy as the heat and beat. And even there is an old saying. It goes, when theory and experiment converge, one of them is probably wrong. Not only probably, highly likely wrong, I would say. And when even I was a graduate student, I was told that if you knew what you were doing, it would be no longer a research. Actually, this kind of old saying refers to this black box. We would like to know this black box. Once you know this black box, namely function f, then you see by controlling these variables, you can determine the properties or performance of a device or thereof. So is there no hope? Looks hopeless. But from our century-long experience, now we know what occupies this black box. We know how it works. Actually, even though there are so many variables, we can sort out, number 1, thermodynamic variables, which are composition, temperature, and pressure. And then all the rest, including even these thermodynamic variables, may be called processing variables. And from our experience, we know that processing variables mostly controls microstructure, okay? And the thermodynamic variables controls defect structure. And then, consequently, the even properties or performances can be classified into 2 groups. Number 1, microstructure sensitive properties or performances. Examples may include mechanical properties, thermal properties, etc. And another one is defect structure sensitive properties, which include most of the functional properties, including, say, chemical property, electrical property, magnetic, optical, etc. So here, this dotted line means not so directly, but implicitly or indirectly affects the microstructure properties. Even thermodynamic variables indirectly controls the microstructure or affects microstructure to determine microstructure sensitive properties. Likewise, these processing variables also control the defect structure. But what I'm saying here is that defect structure is mostly controlled by thermodynamic variables. Okay? And all the rest variables can control the microstructure. So actually microstructure control is more difficult than controlling the defect structure. So now, our ceramics business is no longer bake and shake business because we know this causality, say, between the variables and our properties or function or the function of our devices. So by controlling the thermodynamic variables, you can control defect structure, and then you can adjust or control the all the functional properties. So this reminds you of the minus first law of thermodynamics. You see, suppose that you have the C component ceramic materials. Then what are the thermodynamic variables? Okay, temperature, pressure, and the chemical potential of the C-1 components, or in other words, in the composition. Okay? So once you fix the temperature, pressure, and the composition, then all the equilibrium properties is fixed by that black box, which is now called function. And what are the independent thermodynamic variables? I'm sure most of you understand the Gibbs-Duhem equation, namely relating the all-intensive variables of your system, namely temperature, pressure, and chemical potential of each component. Once you are playing with the single-phase system, then you see due to the presence of single Gibbs-Duhem equation, you end up with the C-1 composition variable and the temperature and the pressure. Those are thermodynamic variables which you have to control the thermodynamic equilibrium properties. Likewise, by controlling these thermodynamic variables, you can control or adjust the defect structure, which decides all the functional properties of your ceramics. So therefore, our ceramic business is no longer a bake and shake business. But still, I have to confess that microstructure control is not so simple as that of defect structure, I believe. Okay, so in conclusion, we may say that ceramics is the combination of body and its soul. I mean by body, shape, and soul, I mean by its function or property. So this function can be determined by defect structure engineering, and the other body or shape can be controlled or made by microstructure engineering. Let me show you one very famous painting by Michelangelo. This is the creation. Now you know what it means, right? The God made body, okay, by virtue of microstructure engineering. And then the God whistles into him the spirit or his soul by defect structure engineering. So this is the whole business of ceramics. Okay? Okay, then what are defects? What are defects? Defects is defined as any deviation from ideal crystal. Then you have to understand what ideal crystal is. Then it is quite easy to sort out what defects are. Ideal crystal, let's say, let's take the sodium chloride like the binary ionic solid as an example. So let's assume that its ionic charge state is just the monovalent, okay? Positive ion and the negative ion. For the case of the sodium chloride, its structure, ideal structure looks like this. Actually, sodium itself, it makes its own face-centered cubic structure, and chloride ion also makes the FCC lattice, and those two positive FCC and the negative FCC made interwoven to make single FCC lattice, and which looks like this diagram here. Okay, now let's project this structure down onto the plane to see more clearly how ions are distributed. Now you can see positive ion, negative ion, positive ion, negative ion. Okay, we can say that this sodium chloride structure consists of, say, monovalent cation site and monovalent anion site and neutral interstitial site. So MX structure actually consists of these three sites. Okay? Now what is important is the charge. In this ideal crystal, cation site, for the case of sodium chloride, cation site should be singly charged. Anion site should be singly negatively charged. And the interstitial site, no charge because it's empty. Okay, then what is the ideal crystal? Ideal crystal may be a bit jokingly expressed in this way. There are what should be there. There aren't what shouldn't be there in the infinite space. Okay? Actually, ideal crystal is defined like this. You see, cation should sit on its own cation site. Now you see, have a look at this red dot. And anion should be on the anion site, okay, which is the negative charge. And the interstitial site should remain vacant. So you see, M cation on M site, X anion on X site, and the vacancy on interstitial site. So this makes the ideal crystal, okay? This M on M site is what should be there. And here vacancy, what should not be there. So this makes the ideal crystal. So actually ideal crystal, you see, consists of this regular structure element. We call this kind of things the regular structure element because it is the element of constructing a whole structure. Okay? Now the ideal crystal, by definition, should fill up the entire space. So you can imagine that ideal crystal looks like this, filling up the entire space. Okay, then we can easily sort out what defects are. As I said, ideal crystal consists of the regular structure elements filling infinite space. Here I mean by regular structure element, say cation on cation site, anion on anion site, and vacancy on interstitial site. Now defects is anything causing deviation from this kind of ideal structure. Okay, let's sort out the defects, say, just from the lattice point. Okay, now there used to be a cation here, but now this cation is missing. So this is missing cation. Okay, so missing cation is represented here by vacancy V. Okay, its actual charge is just 0 because there is nothing. Okay? But this vacancy is now sitting on the cation site, which should be positive one charge. Okay? And another kind of defect can be easily sorted out. Look at this. Now we used to have the cation here. So this may be placed on the interstitial site. Now interstitial site, if ideal crystal, it should have the no charge, 0. But now monovalent cation is now sitting on the interstitial site. So this is called the interstitial defect. Okay? And then the third one on the cation sublattice. You see, this cation, actually, this site was originally occupied by anion. But cation may replace this anion. So anion site, should be taken by -1 charge. But there you put the monovalent cation. So we call it the misplaced defect, misplaced ion. So same thing can happen to the anion sublattice, namely missing anion interstitial anion, and misplaced anion. And even there furthermore, say fluorine cations on cation side, namely, cadmium on sodium side, which makes the impurity defect. And also the stranger ion on the anion side. Okay? So this is also impurity defect. So that's all. Can you imagine anything else? That is exhaustive. So let's summarize once again. So these defects take place on each, say, lattice point. So these are called point defect, okay? So missing cation, interstitial cation, misplaced cation, and missing anion, interstitial anion, misplaced anion, and the impurity replacing cation, and impurity replacing anion. What else? Oh yeah, there are impurities on the interstitial sides, yes, which also make the defect. So they, as I said earlier, they take place on the lattice point. So those are called point defects. Okay? Now, suppose that this interstitial defect lined up to make an extra plane in the lattice, in the real lattice. Then this makes the additional plane here. Then you can see the end of this additional plane. This makes the dislocation. And now you can see the all lineup of the, these atoms. So this is called line defect. Okay? And actually, the ideal crystal is supposed to occupy the entire space, but nothing is infinite. Anything, is finite. For the case of material, a piece of ceramic, it is, first of all, has the finite volume. Therefore, it has the surface. Yes, surface is also defect. Okay? And then if you look even more carefully into the inner structure, then you can immediately see that there are so many grains neighboring to the next grains by creating grain boundaries. Yes, grain boundaries are also defect. So this kind of planar, this kind of the two-dimensional defect are called planar defects. Okay. Okay, and what? Anything more? Yes. Now, let's consider that the vacancies are condensed to make, one void like this. Okay, or interstitial can, assemble into a kind of inclusion, as you can see, somewhere here, inclusion. Yes. So these were voids and inclusion. Which these defects take the three-dimensional volume. So therefore, these defects are called volume defects. So there are actually, four kinds of defects: point defects, line defects, planar defects, and volume defects. Now, in this course, defect chemistry, we pay most of the attention to the point defects because they are thermodynamically stable. And the other defects are not thermodynamically stable. Now you know why. Okay, here is the reason why only the point defects are thermodynamically stable. Let us suppose that we are generating vacancy out of the perfect lattice. Well, you see, you have to cut this bond here. Okay? What does that mean? Cutting bond to take this ion out. Okay? This means you have to work on the system. Working on the system means the increase of energy. So suppose that you need a energy, namely in this case enthalpy. Okay, just a small h. So you need a h to make one vacancy, for example. Then when you make the n vacancies, you have to supply to the system, see, n times h, energy, as big as this much. As a consequence, the system of your overall system has increased. Energy increased. Oh, it is prohibited in thermodynamics, right? But by making this kind of point defects, you are increasing computational entropy in addition to the small vibrational entropy generated by making one point defect here. Okay? Let me tell you the origin of this vibration frequency. Now you cut off the this bond here, right? Therefore, the ions surrounding this defect, its vibration frequency is getting a bit slower. Let's call it nu prime. Okay, so the vibration entropy due to the single point defect is approximately represented by this simple expression. So the magnitude of this vibration entropy is really close to 0. Okay? You may neglect it. But computational entropy, this is really huge because, suppose that you have the, n lattice site. Now you are going to distribute, see, small n point defects. Then how many distinguishable ways can you distribute your point defects? That is actually due to the Boltzmann equation, you end up with the computation entropy as big as this much. Here, K is Boltzmann constant. Okay? So this entropy times temperature, this corresponds to the energy. Okay? This is introduced again to your system, but in negative way. Therefore, total free energy change of your system upon creating n point defects can be written by this well-known equation, namely delta H minus T delta S equals to Gibbs free energy change. Okay? Now suppose that your temperature is 0, then you end up with the only enthalpy term as the Gibbs free energy change. Therefore, no defect can be made in any case. But as temperature increases, T delta S, this term starts to become larger than enthalpy term, eventually to make the Gibbs free energy change negative, namely decrease in Gibbs free energy. That is the natural direction of change, isn't it? Anything in this universe, changes in the direction of the decrease of Gibbs free energy. So at the equilibrium, Gibbs free energy should be minimum. Okay? Now, Gibbs free energy, as you know well from the thermodynamics, is a function of thermodynamic variables of your system, namely temperature, pressure, and combustion. Okay? Then with respect to the number of defects, your Gibbs free energy should be minimum, namely the first derivative of Gibbs free energy with respect to the number of defects should make 0. Now finally what you get is the equilibrium defect concentration or number of defects in given volume as a function of temperature, pressure, and combustion. This looks exactly like a minus first law of thermodynamics, does it? You see, I told you that the thermodynamic variable of your system is temperature, pressure, and combustion. Now here, point defect concentration turns out to be a unique function of these thermodynamic variables. You see? So in this sense, point defects are thermodynamically stable. Then what about the higher dimensional defect? For example, say line defect. Here, dislocation. Now have a look. This dislocation means a lineup of the vacancies or interstitials, if you like, to make extra plane or to make the deficit of this plane here. By aligning, to make a plane, computational entropy should be negligibly small. Therefore, even at the melting temperature, of your system, your T delta system can hardly exceed enthalpy term. Therefore, higher dimensional defects, are normally not stable thermodynamically. So only point defects are thermodynamically stable. Okay, the other higher dimensional defects are not stable thermodynamically. So in this sense, you see, by controlling, thermodynamic variables, you can control the defect structure of your system. And then consequently, all the defect structure sensitive properties can be controlled by these defect concentrations, which is in turn controlled by thermodynamic variables. So this is how defect structure sensitive properties can be controlled by adjusting defect structure via thermodynamic variables. Okay, that's it. Thank you so much. So this is the that's all for the first lecture, and I hope to see you again in the next lecture. Thank you. Bye bye.